in this lesson, I'm going to be talking about electromagnetic radiation. Now, you might not think you've ever experienced electromagnetic radiation, but actually you're experiencing it right now by watching this video, by heating up your hot pocket, by listening to the radio, by doing anything that you do on a daily basis. You are using electromagnetic radiation. So one example of electromagnetic radiation is light. So the fact that you can see all these gorgeous colors on this screen, hopefully, is because of electromagnetic radiation. Visible light, what you can see, all those gorgeous, that rainbow of colors, that is a form of electromagnetic radiation. Another form of electromagnetic radiation is microwaves, radio waves, infrared rays, UV rays, right? When you get sunburn, it's because of the sun, the UV rays, X-rays if you've ever broken a bone. So looking at this, there are three different quantitative values I can give for this waves, this electromagnetic radiation. The first one is wavelength. Okay, so the distance, wavelength, is the distance from one crest to the next. So if you look on the left-hand side, far left-hand side of these waves at the very top, those have the highest wavelength because there's the greatest distance between your crests or your peaks. Okay? And the unit for that is going to be meters. Now, the ones on the right-hand side, they have the shortest distance between those crests, those peaks. And so they have small wavelengths. Now, the symbol for wavelength is going to be that lambda symbol right there, and the unit is meters. Now, frequency is the number of times a crest, so that peak, will pass a point in 1 second. Okay? And so the unit for frequency is hertz, or seconds to the -1, which we'll address in just 1 second. But the representation in a formula we're about to use is that new symbol. It looks like a V. All right, so we've got wavelength, we've got frequency. The last one is going to be energy. So if you notice, when you have large wavelengths far to the left, those are lower energy, while if you have very short wavelengths, then you have high energy. Okay, so if you look even just at red versus violet, red light has the lowest energy but the largest wavelengths, while violet light has the highest energy but the lowest wavelength. So let's talk about the relationship between these two, wavelength, frequency, and energy. How are they related? Well, wavelength and frequency are inversely related, meaning the higher your wavelength, the shorter or the smaller your frequency. So for example, if you look at the very top again, on the far left, those have large wavelengths, but the number of times that a crest is going to pass a point, that's going to be much less than as you move to the right and you have higher frequency. So wavelength and frequency, when one goes up, the other goes down. So that's an inverse relationship. Now frequency and energy, the higher your frequency, the farther to the right you are on that graph right there, the higher your energy is. And so they are directly related to each other. Okay? And so wavelength and energy are going to be inversely related. The lower the energy, the greater the distance between those crests. So let's numerically talk about this. The formula for relating frequency and wavelength is C equals lambda times nu. All right, C, what is C? C is your speed of light. C is 3.00 times 10 to the 8th meters per second. So no matter what the wavelength or the frequency is, the speed of light will always stay the same. The wavelength, represented with that lambda, the units for that are meters. Okay? And then frequency, the units are going to be either seconds to the -1, because it's the number of times per second, or hertz. So those units are interchangeable. So let's look at an example. Here I give you the frequency, so we're going to use this formula. I know that my speed of light is 3.00 times 10 to the 8th meters per second. Okay? That equals, well, I don't know what lambda is right now, that's what I'm solving for, times my frequency, which is 1 times 10 to the 14th seconds to the -1. And so to find my wavelength, I'm just going to divide both sides by 1 times 10 to the 14th, and I get 3 times 10 to the -6, and my units for wavelength are meters. So really quickly, the last thing that we're going to be talking about is what happens with electrons, because while we've been talking about electromagnetic radiation, what I haven't shared is the fact that electrons can move from one energy level to another, and in doing so they can actually release energy, they can release electromagnetic radiation. And so one of the terms you're going to hear when we're talking about electrons moving is we're going to be talking about that energy being quantized. Now, quantized means that the energy that those electrons can either absorb or release when they move energy levels, it is a very specific amount, all right? And so the energy, when it is released in the form of particles, and those particles we call photons. So let's make sense of all of this. Let's use an analogy. Here you've got a bookshelf, okay? So n equals 1 represents an energy level where your electrons are, okay? And they're closest to the nucleus. N equals 2 is the next level up, then n equals 3, then n equals 4, then n equals 5. Notice I can't put books in between n equals 1 and n equals 2. It has to be on that shelf with that specific energy. And the same thing applies for electrons. Electrons can be in the first energy level, the second, the third, the fourth, the fifth, but they can't be in between. And so when they move from n equals 1 to n equals 2, or from n equals 2 back down to n equals 1, there's a very specific amount of energy that's required to make that transition. It's not going to be an in-between energy. It's quantized. It is very specific amounts of energy to go from n equals 1 to n equals 2, from n equals 1 to n equals 3, etc., etc. All right? The other thing, notice that as you move out, those energy levels get closer and closer together, just for you to note. So, moral of the story here, we've talked about electromagnetic radiation. Okay? When electrons move from higher energy levels down to lower energy levels, so for example, n equals 5 to n equals 3, they release a very specific amount of energy. That energy is quantized. Now that energy that's released, we call it photon. We call it a photon of energy, a very specific amount of energy that's released. Now, how do we see this? Why do we care? Well, we care because it allows us to create what's called an atomic spectra. If you look at all of those different little lines that's on the black graph on the far right-hand side for each of those colors represent specific amounts of energy. Each photon produces a specific wavelength and therefore a very specific color. So if we excite, for example, barium, the color you would see without dividing all of those colors up using a prism like they do in this diagram, you would see green. However, that green is made up of all of those individual, the blue, the green, the yellow, the orange, all of those specific colors that are produced when electrons release specific amounts of energy. Okay, so we've been talking about electromagnetic radiation and atomic spectra. This brings it all together. The fact that when electrons jump from high energy to low energy, they release specific amounts of energy. That energy we can actually see because it is visible light. And so we see specific amounts of energy in the form of specific different colors if we were to take that flame, that barium flame or that strontium flame, and use a prism to divide up all of those colors to be able to see what's going into that one flame.